This is Galactic with a supplemental presentation having to do with our study of Unimetrics, which is basically the study of curvature in a mathematical and geometric reformulation, utilizing the power of our number system in a way which was overlooked for centuries and actually millennia. Although we do use fractions, we just never understood that that's actually a different number system that we're using that's not linear. That realization produces a tremendous breakthrough in our understanding of mathematics, numbers, geometry, and physics. So it is significant. Now, the purpose of this presentation is to introduce ourselves to a very interesting concept called infinity. It's extremely important to have a thorough mastery of the concept of infinity. And it'll also provide you as well as the necessary wisdom that you need. And this is literally true. This is a form of wisdom to understand the riddles and conundrums and paradoxes all having to do with infinity. There are dozens or perhaps even hundreds, depending on how you count these paradoxes, all having to do with infinity. By the time I'm done with you here right now, in this very brief presentation, you will be able to solve all the paradoxes that have ever been invented by the mind of man that have anything to do with infinity at all. I don't care if it's Bertrand Russell or anyone else who's formulated these paradoxes, including Zeno's paradox. Anything having to do with infinity in terms of mathematics is very easy to decide if the term is being used correctly or not. And once you know how to define what infinity is, you'll never be mystified again by any of these paradoxes. It'll be transparent to you, and in any room full of mathematicians, you'll be the only one who will get the right answers. And you'll always be able to win any contest, because nobody, to the best of my knowledge, has ever defined infinity. Now, of course, there have been many attempts, and in fact, it's a whole branch of mathematics devoted to studying infinity, which very quickly gets into philosophy and into mind-boggling whirlpools of quasi-logic. On the internet now, you can listen to wonderful, eloquent mathematicians. I just heard two mathematicians being interviewed by Brady Haran, who's an excellent interviewer. He's just a very good scientific presenter, in my opinion. And he lets these men have free rein, and the people he gets on are just amazing. Zvezdalina Stankova, if I'm pronouncing her right, is one of his illustrious guests who introduced me to inversive geometry, for which, if I ever see her, I will feel an affection for her. That is that strong. First of all, she's Slavic and nice looking, so that never hurts. So what is the true meaning of infinity? It's remarkably simple, and once you hear it, I'm sure that you will never forget it. But to introduce this little discourse on infinity, let's try a let's try a little quiz here. We all like quizzes, don't we? You know, you get a multiple choice question, something really capture your interest. Let's see if I can get something on the screen for us here. Once I highlight the right thing. And let's see what we have here. All right, here's our question. Select all the answers that are true. Infinity is, and now there's a list of I believe that's 8 choices that I just invented this test. Infinity is A, irrational, and then listing all 8, irrational, imaginary, countable, uncountable, transcendental, algebraic, mathematic, geometric. Select all the answers that are true. There are 3 right answers in that list. Infinity is mathematical, and it is geometrical, and it's imaginary. None of the other statements are true. So, we then need to define what infinity actually is in a mathematical, geometrical way. What about imaginary? This is an interesting term that we apply in mathematics, but the way we use the word imaginary or imaginarity in colloquial everyday speech, it's something that's unreal. Now, in mathematics, already you're dealing with that which is unreal. Numbers are, of course, not real. No matter what mathematicians like to philosophize, they're twisting the standard use of the word real whenever that word is used of numbers is totally inappropriate. Numbers are abstractions, and that's good enough. Now you know what numbers are in the broadest class sense. They're abstractions. They're not real. Abstractions are not real. You can play around with words, and we're going to find out that Ruger Josip Bošković was up against this as well. He was able to detect the illogic in other scientists' axiomatic formulations and their offers of definitions for things. He was on top of things, and he was able to criticize both Leibniz and Newton quite equitably, and Roger's a very good read for that reason, although he did write back in the 18th century, and it's the way men communicated in those days does not bear much resemblance to how we communicate today, so it's a real challenge. So, all right, what is infinity? Well, we gain our original perception of infinity when we're children, and this is uniform. This is everybody is the same in how they learn about infinity. You always, and as a child, I doubt there are any exceptions to this. Of course, with humans, you just never know. There's always exceptions, but besides the exceptions, the standard way of encountering and learning about infinity is by looking into outer space and exercising your mind the way all children do by asking yourself, what's at the edge? It's instinct, so it's nothing to be embarrassed about, and I've never heard anybody talked out of this. It's like we all enjoy this mind stretch of what's at the end of the universe, what's at the edge. Well, if you say that there is no edge, then you're saying that it's infinite. So that is our first conscious contact with this concept. Infinity. It's quite difficult to define, and you can try to do so if you wish. Many men have, but it's actually a catch-22. You will be involved in a circular argument if you try to define infinity in terms of spatial extent, which is how we conceive infinity originally in our minds. Before we learned mathematics or any higher form of abstract thought, infinity is quite simple. It's the edge of the universe. But, of course, that is a logical contradiction just by saying that it has an edge, because anything that has an edge has an outside. So this is a interesting puzzle to think about, and it does not have an obvious answer. Well, if it had an obvious answer, we'd probably all know it by now through education. Because that's the great thing about science is once you get an answer, you can share it because it's provable. So what is infinity? Um, Judging by our perceptual system, we adjudge in our own minds what is infinity by looking into outer space and asking ourselves the question, either what is the edge, or is there an edge, or is there something beyond the edge, or what is the edge like, or really how far can we see? The technical answer is we're not sure how far we can see. We are always reasonably sure of how far we've seen so far. And the advent of the discovery of the CMBR, the cosmic microwave background radiation, has given us a possible first bit of evidence of there being an edge, because it looks like the cosmic, I'll just say CMBR, it looks like it comes from all directions, which would mean it's coming from the edge. However, that is actually going to turn out to be an optical illusion. The CMBR is just raved about, is just unbelievable proof of the Big Bang. Not true, of course. It's all hype. But it does give us an interesting thing to think about, whatever the CMBR is. And it may be nothing more than static from our own galaxy. That is a highly viable theory, that it's not from the edge of the universe at all. But it could be, and nobody knows yet. We're very young in astronomical science. In terms of thinking about the universe as a unit, that is a natural drive, and so we do it, but it's very difficult. So it does look like it's infinite, doesn't it? Well, that's spatial. So infinity has a spatial quality. We can't define it because there's a logical contradiction in any definition. So literally, it's a strange word, I'll just put it that way. I was searching for the right word to characterize the term infinity. Is quite strange the way it's used, especially by mathematicians. And if you've been exposed to the work of Georg Cantor, about which, of course, there has been a rave, absolute devotion to this rather amazing mathematician in terms of his ability to try to make sense out of mathematical infinity. Well, you can't say that it's a fool's errand, because mathematicians actually need to exercise their minds on all kinds of problems. It's like a dog chewing on a bone. They just, are exercising themselves for when they really find meat. And so they're very interested in games and puzzles, and they really are rather jolly about it, I think. You can get serious about anything, but the mathematicians that you'll see on Numberphile talking about the paradoxes of infinity, you'll find them if you look for it on YouTube. They're worth seeing. Just, I find them quite instructive to see how serious mathematicians think about infinity. Well, there is a great simplifier that changes the whole game, and then you'll never be fooled by these paradoxes ever again, because you'll know what infinity is. This is actually the goal of science, is to make men who know things. Yeah, there could be envy. There's a lot of trouble involved if you're smarter than everybody else, and you better be humble if you are smarter. Don't ever try to lord it over your brethren because you can see that you're smarter than they are. That's not how it works. It's not to gain the upper hand on anybody. Oh, humans do whatever they want. Who cares? Anyway, we don't do that because we have moral compass. We have moral scope. We know that we need to stay in bounds. In the emotional department, we follow the 10 Commandments. That's basically how mathematicians and scientists of the highest caliber operate, despite the flaws that we have, and we all fall short. Okay, so let's go on that note. So the right way to conceive of infinity, as I said, it's not easy to intuit until you see the answer, and then it's obvious. So, what is the answer to that test question. What are the proper characteristics out of those 8 choices? Well, I did use the word geometric, and I do tout myself as someone who teaches geometry, so let's start there. What would be the geometric definition of infinity? Well, the basic one is the one every child learns right away. That in any direction you look, this would be spherically from Earth, or from any orientation where you're at the center, which you are, and therefore you are a point center geometrically, so spherically out from your point. The reason we say point of view. So that is a spherical direction, correct. So the first thing you learn about infinity is that it's spherical. If you're talking about space. And then there are footnotes everywhere. Of course, this has been going on for centuries. We don't want to go down the well-worn path, the beaten path of the things that men say every single generation. We don't want to be tedious with this. We want to get right to the point. But it is interesting that our first perception of infinity is spatial, outer infinity. And it's important to say outer, because there is such a thing as an infinitesimal infinity going in. We haven't gotten there yet. That's jumping ahead, actually, but we'll get there. So there are basically 2 forms of infinity if you're looking at things spherically. But we don't think of the inner infinity, which would be the infinitesimal, what we call a point. We don't think of that as a candidate for infinity, although mathematicians do, but just looking at things geometrically, this is at first blush. This is when we're kids. This is how we first encounter infinity, is spatial. Later we learned that numbers can be composed into what's called infinite sequences, and there's other ways of treating the term mathematically. But in the basis, in reality, we only know of one infinity. The infinity of space going out. That's the original perception of infinity. Well, what is that? What can we say about it? The key word is that it's imaginary. And that's the proper word for it, although imaginary has the connotation of unreal. We're not using the term imaginary that way. It's rather a boundary. It has to do with a boundary. That it's what's past what you can see. That would be infinity. Unless you can prove that there's an end. But if you can't prove that there's an end, then you have to assume that you don't know. Which means that puts the whole question into the realm of the imagination. You simply cannot imagine the edge. That's why it's a paradox. So we have to accept that. It's very important in science to do that. You could say it's tentative, but it is important to realize sometimes that we are physiologically hampered. And there are certain things that we might be able to perceive, you could say indirectly or incompletely, where we become aware of our limitations, basically as cellular organisms of our size, scale, and where we are. We simply can't see as far as we would like. But what is beyond the visible limit of the universe, whatever we've been able to measure to whatever distance, we know that there's more yet. We haven't found any direct evidence of there being an edge, although there is an extrapolated edge, as you well know. That has not been proved, and even if it has been proved, it doesn't solve the paradox. So, infinity is imaginary space beyond what we can see. Now, could that be given a number? If it could, then infinity would have a mathematical context if it can be given a number. Well, nobody's ever been able to do that. And all the work of the set theorists was totally in vain. They are actually attempting to do that which cannot be done, which is to make the line of numbers, the number line as we abbreviate it. They wanted in the 19th century, and still want, to treat the line as being continuous. That's the whole reason for the so-called real numbers and for set theory. And it's in set theory and related issues in mathematics having to do with infinity that produce this amazing volume of paradoxes, which are all essentially the same. It's really amazing how our mathematical intellect and imagination can unite to tackle a true paradox. And it has to do with what you're trying to force out of the word infinity. This is a typical error in science which you should learn to be aware of, is the desire. You don't want to point the finger or create a sense of blame or guilt, but this is a distinct error that scientists fall into, especially now, that just because you have a term that's been useful for you in some way, that you know everything there is to know about it, so that when you use it in a new context, it'll be the same. In the case of infinity, that's not going to work, because infinity is one of the most, well, I'll just say it has an amazing characteristic that I don't know of any other term except for infinity that has this peculiarity to it. Because it's such a fluid concept, if you let it be, such as infinities of infinities, and certain paradoxes which are very old, such as I think it's Hilbert who came up with the hotel paradox. These are transparently, and they're absurd. They're transparently absurd nonsense puzzles. Once you know the secret of infinity, what makes it so peculiar? So that's what we're going to see today. Let's get to the construction that actually solves this. When you look at infinity strictly geometrically, you can see that it's just one thing. It's the outer extent of space that we can't measure. So it is immeasurable. Why is that? Shouldn't the universe be finite? Is it finite? Is it infinite? Of course, this is a question that's been asked literally forever. Well, not literally forever, but... So could that possibly be mathematized? Could there be any possibility of dealing with infinity with mathematics? This is equivalent to saying, can you turn infinity into a number? And the answer is yes, if you're only talking about space. If you're talking about spatial extent, you can solve that puzzle of infinity with a very interesting trick. And it is a trick. But it's a curious trick because it undoes the trick we play on ourselves by saying the word infinity when we can't define it. What if you could define it? Let's pretend that we can, and we'll call it the lazy 8. All right, what is it? We're saying that it's the number for infinity. But here we're saying very specifically that it's not a quantity. It's simply a number because we say so. And in order to define this number numerically, there is an ancient trick that you can use to bring this candidate number out of the closet. So let's see what it really is. What do we want it to be for one thing? We want it to be the number that represents the spatial infinity that's beyond the edge. Well, then you're going to have to invent an edge. It turns out we already have that construction built into our number system. When you see a fraction, you know it has three parts. That's actually the proportionality operator. We call it division for historical reasons, but it has nothing to do with dividing anything. And in one context, you could force it to have that meaning, but that's not the native meaning of a fraction. A fraction is a relationship. Linear numbers don't have relationships except one, distance. But we're going to be using a different number system, and I hope that you've kept up with the last few presentations at least. Otherwise, this is going to come as a shock to you, but we simply switch number systems to the correct number system and leave the linear number system behind, because we're not dealing with linearity when we're dealing with infinity. Infinity is spherical. We just proved it. It's the part of our spherical environment, which we call the universe. It's the part of that sphere that we can't see, and it is a sphere. There's no question about that, because everything we see is in spherical space. So if there's something enclosing the spherical space, we literally cannot imagine it, although I'll show you later we actually have to if we want to fully understand space-time. But that's in a future presentation. For now, I want you to get a handle on infinity by using the fractional system. As I taught you, when fractional numbers are composed on unity as reciprocal representatives of the number 1, for instance, 1 over 2 and 2 over 1, multiply to 1. Well, that makes one number out of 2. So the 1/2 and the 2 over 1 are a pair of numbers. And this is the same format that's used in complex numbers. A two-componency is all it is. It's just two numbers that represent one number. So you have to ask yourself, what is the one number that it represents? But you also have to ask yourself, what are the two component numbers representing? Well, those are the two quantities that are in proportion. A proportionality is mutual, but the order is important, so it's not commutatively mutual. So a proportion is an interesting term to use, where 2 over 1 times 1 over 2 produces unity. A very interesting thing when you consider that one number isn't even a whole number and the other one is obviously greater than unity, but they do have this relationship that is not additive. It's multiplicative. So the identity for multiplicative space is 1. Now, what that means is you can construct a number space for spherical space. That is, the spherical space has its own number system using exclusively linear numbers, but in this reciprocal relationship. Now, we were able to prove that that is actually consistent, that those are actually the linear numbers we've come to know and love, 1 and 2 in this case, but in their relationship, they do form a different geometrical object than is possible with a single component number. A single component number can only exist on a line. The more you review this in your mind, the more you'll find it to be watertight. But this is a very important transition, because we cannot lose linearity even in spherical space. It has to be consistent. So it is. It's quite interesting. So we've been talking about the circle, but as I've told you, the circle is almost identical with the sphere. There's a very simple geometric and mathematical relationship between the circle and the sphere of that circle, such that we call it the equator of rotation. Every sphere in the universe rotates. So So that would be on the equator that we would measure the centrifugal force. And that's the right term for that rotation. It produces centrifugal force at the equator. That's on an integral, but it can be shown that that is the case. So the circle has a basis number of 1, such that the circle itself represents the number 1. Just as the line has a center point, which has a numeric value of 0, so does spherical space have a center, but it's a spherical center, so that the center is actually a sphere. And you might ask, well, what's inside then? We're just about to find out. Because if you do decide to define infinity correctly, so that you finally get it and never need to worry about it again, and then can use it correctly, this is the way to do that. You take infinity, and now you define it as spheric spatial infinity, according to the definition that we declared, that it is past the boundary of what we're able to see, which is to say, to measure. So it's outside the sphere of the universe. So we're artificially declaring, axiomatically, that the universe has an edge. But we can't just throw out infinity, and so we give it a number. And this is how we define it. We use that little line that's between the two fractional numbers. And just think of it. This is not to say that that little line is the edge of the universe. But we're actually going to say that there is a boundary that is that line in the fraction. That line defines the edge of the universe. It's neither of the numbers. It's what's between the numbers that's the edge. So we're defining the outside and the inside without saying anything about the edge, except that it's the surface, it's actually the outer surface of the spheric universe. Now it turns out, and I'll just say this in advance, so I could say it later or now, but I'm just going to say it now. What this will turn out to be is that the edge itself is infinity, so that the concept of the edge becomes a matter of syntax, such that you don't need to talk about the edge because it is implied. It's implied this way, that what is on the outside is the number on top. And that's imaginary, and that's the key to everything. It's also the key to imaginary space in the complex number sense. This solves for the need to use complexity at all. We don't need quaternion algebra anymore, and we don't need complex algebra anymore, because we're going to prove that this builds that concept right into the system such that complex numbers become redundant. We can use rational numbers to compute in spheric space. That'll be the result of the operation we're about to complete. So what's the number on the bottom if the number on top is infinity? Infinity is outside the edge. What's inside? Unity. So it's spherical infinity over 1, and that's the edge. And what is absolutely critical here is that number is imaginary, which means, according to the correct way to define geometric mathematics, which is to say mathematics and geometry in general, the correct way to say that is that the universe has a value, and it's 1. That's what's inside the universe, is 1. So this imaginary number relates infinity, which is outside, to unity, which is inside. And that's the definition of the universe. When you decide to finitize it, this is the correct way to do it, while maintaining a consistent attitude towards infinity, which we're treating as real. And in order to treat infinity as real, we have to make it imaginary. That's not a contradiction, and this may be one of the most amazing, mind-bending tricks that you'll ever perform to get on top, to understand things when others don't, so that you'll be the chief scientist. No more sand kicked in your face, because you'll know what infinity is when no one else does. So that is our definition of infinity. Now that number is useless, it's imaginary. And and what I was going to say is, in geometry, you can't use imaginary anything. It could be physically imaginary in the sense we can't see it. That would be infinity. So that is the perfect use of our natural use of the word imaginary. But what we're going to prove as a second step is, by doing this and declaring that that number is imaginary, you're getting complexity into the space. Do you know what complex numbers are used for? The only reason they exist is to get a spherical function into linear space. That's true. The same as the calculus is used for that reason exclusive. That's the only reason for these tools, is to try to do something with curvature, because our linear numbers can't do anything with curvature. So we need the calculus and we need complex numbers. Not in the spheric number system, and you don't need either one. The space is already integrated. It's integral linear space, so none of those problems exist. You're looking at pure curvature. So, knowing that all of this is consistent with our new number system in geometry, we're going to axiomatize the universe, physical space, this way, by observing that it is spherical, no question about that. And so all we have to do is put infinity outside our universe, because our universe is finite. It has to be, or we can't compute anything. We think we can get away with computing the universe because we think we've computed its origin. That is not necessary to do that. In fact, if you insist that that has been proved, it's the correct model, and that it's true, you'll never get anywhere, because you went right over one of the biggest mistakes ever made in the history of science. And all of our top scientists are guilty of it, and they simply don't realize what they're doing to themselves. Well, someone had to come along to break that logjam. Now we know that the spherical number system is composed of reciprocal numbers. Whole unit numbers and whole unit fractions in reciprocal relation on unity. That completely defines spherical space. But we also learned that those two numbers are geometric numbers, such that the 2 is representative of space outside, because the surface of the sphere is 1. So whole numbers greater than 1 represent space going out. That's consistent. The space going in towards the center are the fractions. And this is the solution to Zeno's arrow paradox. So we're already starting to solve, this will solve all the paradoxes that have to do with infinities. Because now we know where it is. But it's in more than one place. Because of the reciprocal relationship in the spherical number system, the edge number has a reciprocal. And since that's the edge, this represents outer space, that the infinity is on top, meaning it's outside, whereas the 1 is inside. Well, when that's inverted, the infinity is inside the center. Instead of being outside the edge, it's inside the center. That is absolutely true, and you're the one who needs to change. you're going to have to force yourself to see that and accept it and rearrange everything inside you to cope with that. Because this is the replacement for zero. There is no zero. There just isn't any such thing, except in one extremely restricted sense. The additive property of linear numbers requires an Archimedean center, and we know what that number is. That has nothing to do with reality. That's a pure fantasy, and that can be proved. I've proved it. Because that linear number system that we're using currently in science is the derivative number system of the actual number system of the universe. So when we compose these fractional reciprocal numbers on unity, we're actually composing real space. And what that means is the entire system, both mathematically and geometrically, can be completely defined simultaneously this way, by using infinity this way. Instead of 1 over 2, 1 over 4, 1 over 8, or 2, 4, 8, 16, 32, this would be harmonic progression rather than linear. Remember, we're not in linear space anymore. The separations in spherical space are not linear, they're spheric. And they're harmonic. So, just bear that in mind while we go over this, because now we have a center to the universe and an edge. But by composing the center this way, such that it is 1 over infinity, putting 1, you see, here's where it gets interesting in the difference between the edge and the center. Because the center now has a surface. In linear space, the center has no surface because it's 0D. That's a huge, huge hole, directly responsible for the black hole mathematic formulation, which is why it's so silly. Oh, you're going to learn a lot about cosmology. You'll be able to stump everybody from now on once you learn all of this, which I'm going to teach you. This is the way to get a grip on infinity. There's only one infinity in the universe. It's the spatial infinity at the edge. And that is proper, and that actually is the only way to get to hyperspheric space so that we can finally solve the mystery of space-time. This has enormous repercussions all the way through physics, just remarkable. So we now have a surface that is 1 at the center of the universe, inside of which is imaginary space. But in this case, the edge, which we're calling the surface of the sphere, is localized, so that the surface is visible in this sense, that we're looking in towards the center. That's a solid surface in the metaphorical sense. And what's inside is imaginary. It's the reciprocal of the edge number. So it's infinitely small to the proportion that the number at the edge is infinitely large. That implies that there's a limit to numbers, that the number system we just invented is finite. It's a finite number system. What takes the place of infinity is continuity. Continuity is what we're mistaking for infinity. It's been debated for centuries whether space is continuous, and it's never been decided. The same thing holds true for time, and now it's at the top of the list in really reckless debate and reckless speculation and non-scientific, really nonsense, having to do with time because we're so fascinated with it but utterly confused by it. We're also utterly confused about space too, but that only becomes apparent once you know what time is. And you're going to know what time is too. This answers it does. It just answers all the problems in science. Is to begin with a number system that the universe uses. We've been using it. It's just that all of our mathematicians have been too stupid. And that's the right word. They're stupid. All of them are. Only you and I and our little team of know-it-alls are going to know what it really is. So infinity is a chimera. There's only one infinity in mathematics. Only one. The number system is finite, and all the work of Georg Cantor was a complete and total waste. Not for the technological people, it wasn't. They needed all that stuff for what they were working on to make weapons of mass destruction to specification. I mean, we also get clocks and cars and goodies, refrigerators, but actually, the purpose of technology, as you well know, is not something you want to talk about around children or in mixed company. Only men should talk about what technology is really for, because it's obscene, in the highest degree obscene. So that was the work of Georg Cantor and David Hilbert. They were slaves to a communist Nazi system. And that's all they were. And I'm really sick and tired of hearing the names of these mathematicians as if they were heroes. The only heroes are the men who reach wisdom. And if you think that you can juggle infinities, you're a moron. So you're not a leader. And scientists are meant to be guides and leaders. We're the only ones qualified for that job. Not all of us. Don't ever count on that. And don't ever look at me for that, because absolutely not. Anyway, you can now see that there's an infinitesimal number that it's at the center of the spheric space. This solves everything in mathematics and physics, is to realize there's a surface to the center of the universe, has a surface of 1. And that's at the center of the universe. You may see that raises a paradox. But what we've done just by formulating infinity this way, that it's involved in a unit fraction reciprocal number 2 component number. All it is a number for 1. Infinity over 1 times 1 over infinity equals the sphere. It's the infinitesimal sphere, and it does have a radius. And we've actually found it too. And of course, it's in imaginary space. We also know the full extent of the universe, and we've solved for infinity completely. It removes the paradox of infinity. We know exactly what infinity is, both numerically and geometrically. It's only in one place. And it has a reciprocal. That solves the quantum paradox, is the reciprocal of spatial infinity. But there's one more trick and one more secret. You can't unlock the quantum paradox or space-time until you know the cause of time and the role of time in the geometry of the universe, where it is. That'll be in the next presentation. I hope you stay tuned. We'll be right back. Keep looking up, okay? I get a big kick out of this. I'm flying right now. I'm feeling pretty good. So